We're actually going to kick off today momentarily with a video. I feel like we've already been kind of talking about this. So for instance, if I talk about boiling points, let's just say we looked at some compounds. One has a higher boiling point, one has a lower boiling point. What would you say about the intermolecular bonds? Compare the intermolecular bonds between those two compounds. What do you think? The one with the higher boiling point temperature has stronger intermolecular bonds, exactly. And so that's kind of what we're talking about here. We're going to dive into that. But in order to dive into that, we need to understand what it means when something boils. Or what does it mean, the temperature at which something boils. And I kind of feel like it's almost like you're trying to explain something to somebody where in order to explain that to them, they already need to know this, but you can't explain this to them until you explain this. Okay, and that's kind of where we're at. Okay, we're going to be talking more about equilibrium vapor pressures. Well, I promise, equilibrium vapor pressures, a lot. I have a little video to kind of show you what we mean by equilibrium vapor pressures and boiling point temperatures. So let's see what we think. I thought it was pretty good. Maybe. Based upon the video we just saw, it kind of showed the up arrow, that was the vapor pressure of the liquid, and the down arrow was the pressure of the atmosphere. One of the things near the end they said was when the vapor pressure of your liquid is equal to the vapor pressure of the air, then boiling is said to occur. That's exactly what this says up here. When we're walking around this room, the pressure of those nitrogen and oxygen atoms generally is about 31 inches of mercury or 760 millimeters of mercury. Okay? So when we talk about normal, the normal boiling point temperature, that's basically when the pressure, the vapor pressure of your liquid has been heated so much, breaking so many bonds, going from the liquid to the gaseous state, the equilibrium vapor pressure is 760 millimeters mercury, which is the down pressure. Okay, so that's what we call the normal boiling point temperature. So that's kind of a short case, and we'll kind of come back to that. But in the meantime, we're going to talk about those intermolecular bonds. Okay, so boiling point temperature, you guys told me the higher the boiling point temperature means the stronger the bonds. Now, somewhere in there, you're going to have to wrestle with how do we define that? How do we judge strength of intermolecular bonds? Because there's so many things related to that. This actually is a scatter plot of different substances. Plotted along the x-axis is the heat of vaporization, the amount of energy per mole required to break those intermolecular bonds so it goes from a liquid to a gas. And then here along the y-axis is boiling point temperatures. So if you do a scatter plot like this, and if you get kind of a straight line, which is kind of a straight line, pretty much a straight line, then you say there's a relationship as the equilibrium vapor pressure, as the heat of vaporization, the delta H back, as that increases, so also does your boiling point temperature. So I think, I've never done this, but I think this semester I'm going to try something new. I'm going to start to kind of list over here, and again, like our other lists, you might want to come back to it. But with regard to intermolecular bonds, how can you, if you're given, and we're going to be doing this here in a minute, if you're given like a series of molecules, how do you know which one has the highest degree of intermolecular bonds? Okay, first off, I think this is the high on the list, is to say what sort of type of intermolecular bonds. So I'm going to put IM stands for intermolecular bond type, and I'm going to go ahead and hopefully list the types in order of increasing strength. For instance, this is Wednesday. On Monday we talked about ion-ion. Okay, that's the strongest. And then ion-dipole, something that's polar and something that's ionic. And then we talked about actually hydrogen bonding. It's a special type of ordinary dipole-dipole. Okay, and then we went to dipole, induced dipole. And then we went to, I don't know if it's my favorite, my least favorite, that induced dipole, because it has so many different names. Induced dipole, goodness gracious. The induced dipole, where both of the things are nonpolar. To me, you usually start here. What sort of intermolecular bonds do I have? And this is strongest, and this is the weakest. Okay. After that, and we talked a little bit about that, you might move on to this sort of thing. For substances of similar size and surface area, the one that will have the higher boiling point will have the higher degree of intermolecular bonding, and then in blue is the next thing I'm going to put up there. One of the things we did Monday was to look at, and we'll do a little bit again today, look at molecular weight. So I'm going to say the higher the MW stands for molecular weight, the stronger the bonds. They become, I think you can think of it as it increases their polarizability, I think. This is, yeah, I'll go ahead and jot this down. The higher the molecular weight, generally bigger molecule, greatest surface area, higher molecular weight, bigger, better, no, sorry. Higher molecular weight, bigger, more surface area. And then I'm going to introduce that means more polarizable. Okay, because this induced dipole, I hope you got the idea though, even it's the weakest, that all things that are connected together with intermolecular bonds have those dispersion forces. Remember, induced dipole has dispersion forces, London forces, maybe that's about it. Okay, what else we got? So this is with the same type of intermolecular bonding. The one with the higher molecular weight will generally have the higher bonding. Did you say that? So I put higher molecular weight up here. Maybe for the next one, I'm going to say, because sometimes you have things with the same molecular weight. I'm going to convince you of this, but really surface area, as I state right here, is kind of even more important than molecular weight to a certain extent. Although a lot of times they come hand in hand, but not necessarily. So here we have our group, our halogens, group 7A elements. Of course, they're by period, increasing period, so of course their molar mass increases here. They're showing, I didn't know acetine is a diatomic element, but they're showing a diatomic element here. So what would you would expect that the boiling point temperatures to increase as you go down. That's exactly what you see here. We'll talk about melting point. Now, of course, the difference between boiling point and melting point temperatures, boiling point is a better indicator, and I'll kind of remind you of this, of what's going on with regard to molecular bonds. Boiling point temperature, of course, is when it's transitioning from a liquid to a gas. Okay, melting point temperature is when it's transitioning from a solid to a liquid. There's a few players in this that kind of make it not as much of a show with regard to intermolecular bonds, but as it's listed here, it's doing the same trend, isn't it? It will not do the same trend. This is actually a little bit kind of what we looked at the other day. Notice we have analogous, if you look at carbon, silicon, germanium, and tin, they are all in the same group. I'm convince myself of that would be 4A. And in this little example, we're combining them with 4 hydrogens. So carbon, silicon, and tin. So of course, carbon is the lightest, so it has the lowest boiling point temperature. Remember, low boiling point temperatures means that the intermolecular bonds aren't as strong. So somehow it seems like there's all sorts of things you need to just kind of remember how that works. A slide to kind of show you an assortment of, in this case, nonpolar, and over here we're going to look at polar. These are all nonpolar substances. The reason I'm narrowing it down to there is because if they're nonpolar, this is the only sort of activity we have in town if they're nonpolar. They're arranged here already by increasing molecular weight. The whole negative boiling point temperature kind of hurts my brain. I don't know if it's up to you, like with you. The Kelvin scale is easier because you can clearly see it, but remember that the more negative it is, the lower the temperature. So this would be a low boiling point temperature, increasing boiling point temperatures, increasing molecular weight. Increasing heat of vaporization is perfect. So those are nonpolar, and these are polar. Okay. Again, they are organized by increasing molecular weight. And notice we have, and this won't always be the case, but we have a nice cool trend in, no pun intended, increasing, see that naked person now? Increasing boiling point temperatures and increasing heat of vaporization. For the ICL, I'm not sure why there's not heat of vaporization. I ran out of time, but otherwise I'd be like, what is that one? Makes me wonder. So, we're going to watch this video, but it's the same video we watched the other day. All right, so I thought this is kind of neat. This actually, is this right? So it's very cool. So we have period 2, 3, 2, 3, 4, and 5 connected, in this case, with hydrogen. The greenish one is with antimony, with one hydrogen. The greenish one is with 3 hydrogens, and the blue one is with 2 hydrogens. Now let's go on the next. Because we'll move my periodic table. See if we can get this right. So this one is with group 17, that's the halogens. So they're going chlorine. The next one is HF. This would be HF, right? Is it right? Orange, HF. If we look at the green line, it's going SB, AS, HB, AS, P, and then above P is N. So this would be NH3, and this would be FCl. Does that make sense? Makes sense to me. I thought it was kind of clever. As much as I give OpenStax a hard time, I should recognize when they are clever. So what I was trying to say is these are the halogens. So this guy right here would be HF. Okay, this is actually group 5A. So it goes going up SB, AS, P, and so this guy would be analogous NH3. And then this guy, if you find the TE, this is the one we talked about before. TE going up, 6A, Se going up, sulfur, and then this would be oxygen, so H2O. So the downward trend we see for these three has to do with decreasing molecular weight. And you know it's going to show you. So if you go on to fill in the blank for the H2O and the HF and the NH3, why are they so much higher? Yep, because they can hydrogen bond. That's it. That's all it is. I see that's it. But it doesn't have any time
You know, we've got, anytime you can see an OH bond, an FH bond, or an NH bond, then you can have hydrogen bonding. It doesn't have to be just these simple molecules. All right. Switching gears. Now, one of the things I have and I think I've done it other semesters, so I assume it's there this semester too, I think. We're going to talk a little bit about nomenclature. We talked about nomenclature before, but that was for ionic compounds. We're going to dabble a little bit in nomenclature for organic compounds. So for organic compounds, one of the things oftentimes is our organic compound, the ending of our name will say what sort it is. Alkanes are a family, and again, I'm kind of getting ahead of myself a little bit, but alkanes are a cool family that contain only hydrogen and carbon, they're hydrocarbons, and they have only single bonds. So here in a minute, you're going to see these guys, hydrogen and carbon, only single bonds. Eth means one, Eth means two, sorry, fine answer. That means two. Prop means 3, But means 4, Pent, like you might imagine, means 5, and hex means 6. While I'm at it, one more thing is these ends right here means that it's all in a hot dog shape. That just means a straight line, straight chain, I guess is what would be better say, straight chain. So there you have a little bit of naming things. Okay, so the formulas for these go like this. So we have 2 carbons, 3, 4, 5, 6 carbons. We have enough hydrogens to go ahead and what we call saturate it, make all single bonds. So not so surprising then that as we increase the molecular weight, the boiling point temperature increases. Okay, that's it. Like again, the whole negative thing, like which has the higher boiling point temperature between these two? Well, the one that's more negative is the lower boiling point temperature. I just think it hurts my brain. Alkanes, like we just saw, alkanes contain only carbon and hydrogen, and I'll kind of show you what you're going to see here in a minute. They contain only carbon and hydrogen, and they basically then look like this. And did I already do that? Maybe I did this in my homework. I think I got kind of sloppy in my homework, went back to kind of how I learned it in my organic chemistry and some general chemistry. Those dashes, at the end of each of those dashes is a hydrogen. So that is your alkane. That would be what? Ethane. Prop we said was 3, so propane would have 3 of these guys all lined up, surrounded by hydrogens, etc. So even though there's an electronegativity difference between carbon and hydrogen, it's pretty slight. So these alkanes are generally called nonpolar. We'll talk more about that later. So alkanes are generally nonpolar, and so just the increasing in molecular weight allowed for this to increase and allowed for a higher boiling point temperature. Okay. So, but remember, with increasing molecular weight, it's really about the surface area that gets you more bang for your buck, because you figure, and we're going to see that something that's elongated actually has more surface area than something that's wadded up. Okay. So the greater the amount of surface area, it means surface area. We'll call that SA. So more SA, stronger bonds. Stronger or more. Kind of related. Stronger, and the stronger the more molecular bonds, because it's the higher boiling point temperature. All right. Well, what about these? Notice that, again, kind of if we look at nomenclature, they end in A and E, so they're alkanes. But we have the pent prefix. Pent means 5. So in each of these cases, these are isomers of pentanes. So we have normal pentane, which I'm going to show you a picture. Normal means kind of just a chain, what do they say, straight chain. Isopentane is kind of balled up. Neopentane is very balled up. Okay? And what we're going to see with the more balled up, it's, you can see that what happened to the boiling point temperature is it decreased. Decrease in boiling point temperature means less molecular bonds. So here we go. That looks like a hot dog to you. Neopentane, N-pentane, 5 carbons. 1, 2, 3, 4, 5. Okay. Now these, the CH3, you kind of have to picture it as the carbon with the 3 hydrogens branched off of it. The CH2, think of the carbon with 2 hydrogens branched off, etc. All right, so this is kind of balled out. Can you see this? This is isopentane, and this is very balled up. Okay. So what we would call this is, and we're going to use the word branching. So this up here, this N is no branching. And this is some branching. And this is lots of branching. I called it balled up, but branching is probably a more scientific word for it. So I'm going to actually add something then. It's called branching. And basically with the, how do I say this? I'll call it least branching. The least amount of branching and the least amount of branching is going to be your N-type anything, okay, the long thing. Least amount of branching, it means that it's more polarizable. I'll finish that thought. If it's more polarizable, you get more, I'll call them dispersion forces. How's that? Dispersion forces. Say, don't blame me, because up here, induced dipole, I'm going to put dispersion forces there. I don't know why we have so many names for those things. More dispersion forces, it means that it's going to have a higher BP. And that's not where you buy your gas, which means by gas in the phone. But that's boiling point temperature. That's all these slides are going to say. So these actually then kind of show you start to get a feel. I have one more thing to kind of show you the N-pentane, the isopentane, the neopentane. Well, I guess I should add to this. Does this make sense? It's weird that you actually have the most surface area up here. The most surface area with the least amount of branching. So maybe I should say that. Least amount of branching, most SA. With branching comes less surface area. So here they are kind of, you really see when I said balled up, I mean balled up. It's really hard to actually, with this less surface area, induce a dipole momentarily. All right. So for similar substances, those with kind of the same type of intermolecular bonding, hopefully we're okay. When I say same type of intermolecular bonding, this is what I mean. Okay, that boiling points will increase with increasing molecular weight. Got that? If the molecular weights are similar, which they totally were with those 3 different isomers of pentane, then with the branched isomer will have the lower surface area and thus less dispersion forces, and will have what? The lower boiling point temperatures. So this is kind of what I put up over here. Increased branching, less surface area, less dispersion forces. Well, let's see how we do. Because I can guarantee you, like on your, not that I'm not trying to teach to the test, but on your test, your Unit 1 exam, I'm going to try to see from you guys if you can either have this is a set of 3 different compounds, put them in order of boiling point temperatures, or sometimes there's a pair, sometimes there's even 5, something like that. We're going to kind of use this list as a guideline. So we have N-pentane. Now N means it's the hot dog, so it has a fair bit of surface area. Butane means it's got 4 carbons.
We have an isomer of butane, with more branching. So do you guys buy this, that already, between these two, which one would have a higher boiling point temperature? The first one, yep. And then we're gonna kind of put this three, we're gonna take these three together. I've got, pro means three, so I've got another alkane with 3 carbons here, okay? So this would have a lower molecular weight. So the thing comes in this one, these two. Which one will be higher? Do we know that? So I'm going to go ahead and reveal it to you. As it turns out, the 3 carbon alkane actually has the lowest boiling point, followed by the isopentane, followed by the normal pentane. Sorry, butane, followed by the isobutane. But that one would be kind of hard between these two. This would be pretty obvious. This one, this one, this one. Anyway, so. And I'm not going to go on into the next part just because I want to kind of clear the palette from this topic. So, like I said, I think we're going to be fine with regard to time. If you come in one day and you're like, oh my gosh, she's talking a million miles an hour. Well, I looked at our schedule. We're not as good as I thought we were. But these will be due on Friday.